Good afternoon, Venkatesh. We'll start in 3 minutes. Just we are waiting for the other members to join. Okay, guys, it's 3 p.m., so I think we can start now. So, right now we are in the week 4 of this particular week, and like of this particular course. Like most of the half of the course has already been over. So, this is total of 8-week course, and we are halfway through. So, in this particular dot solving session, we'll try to solve your questions based on which you will be easily able to solve the questions which are given in the assignments. Okay. And one more thing before we start, the last day for the registration of the course has been extended. It was before it was 17th and maybe it's 16th, but now it's shifted to the 7th, 19th of August. Okay. So if someone want to, so on this particular date, till last, this is the last date to register for the this particular course exam. Okay. So let's get started. Just a minute, guys. Hello. आप सिक्योरिटी गार्ड को दे दीजिए, पेमेंट हमने प्रोसेस कर दिया है. ओके. जस्ट अ मिनट गाइस, पार्डन. नहीं, हमें कोई ओटीपी रिसीव नहीं हुआ अभी. हाँ, अब आया है. 399400. हाँ, आपको मॉर्निंग का टाइम दिया था, 10 बजे आपने बोला था. ठीक है, आप सबमिट कर दीजिए उनको. सिक्योरिटी गार्ड को दे दीजिए. ओके ओके. Sorry, guys. Okay, then let's get started. So, in this particular week, week 4, the list of the content that we have discussed is as follows. So, we discussed about the impact of the nanoscale on the mechanical properties in the first lecture, and then we went to the superplasticity. So, measure of this particular week was focus on the superplasticity, and we'll also try to solve as much as question possible on superplasticity, which will relate with the assignment questions. Okay, and let me tell you that this particular week, sorry, this particular dot solving session will be more of the interactive. So I will display some questions. If I will try to answer them. If there is any doubt, please feel free to answer it. Question me back. Okay. One more thing, you can always put your answer on the comment box, and if you want, if you are free, then you can unmute yourself and interact. Both the options are favorable. Okay. So before I start, let me ask you that in this particular week for the video lecture which has provided on the NPTEL, do you have any doubt on those lecture of week 4? If there is any, please let me know, and we can have a discussion on that. You can post your question, and also at the end of this particular dot solving session, once it ends, I will again ask that if you have any doubt, please let me know. Okay. Okay. Seems like there is no doubt, and so let's move to the next first question of our dot solving session. Okay, so let me read it for you. Question number one is saying that in the set of the options given below, there are the options are given. Select the one which should be suitable for the superplasticity. So we have to select the options which is suitable for the superplasticity. And in what way? Like grain size, strain rate, and strain rate sensitivity. So we want to find the favorable condition under which the superplasticity can occur. Okay. So if superplasticity had to occur, so let's discuss about the first thing, grain size. So grain size, whether it should be fine or it should be coarse for our material to show the superplasticity nature. So what is your opinion on that? That whether the grain size should be fine or it should be coarse if material is displaying the superplasticity? Yeah, it should be fine, right? Because lower is the grain size, easier their movement can be. We know that grain in the superplasticity, one grain, another grain, they will slide over each other, right? And finer it is, more energy the grain boundary will be having, easier it will be for it to slide. Okay, so we can, in this particular thing, we can select the first option. What about the strain rate? Strain rate should, whether it should be low or it should be high. We are talking about the strain rate, not the strain rate sensitivity. So for material, so let's think from that perspective that if I deform my material very fast, extremely fast, okay, strain rate is very high, whether it will what kind of nature will it show, whether it will undergo the plastic deformation or it will just like fracture in the brittle manner. So if my strain rate is very high, okay, so okay, let's have this particular material, and let us say I'm deforming it at a very slow rate. So in slow rate, what will happen, that it will elongate also compared to its dimensions and all. But if I am drastically increasing the strain rate, so this is low strain rate, if I'm drastically increasing the strain rate, what will happen, that they will fracture drastically. Okay, they fracture like that. Okay, yeah, that's right, Venkatesh. So in strain rate should be very low. Low strain rate is always preferred for the material to show superplasticity. So in order to anything to show the plastic deformation, the strain rate should be low. High strain rate will lead to the brittle nature of fracture. Now let's talk about the strain rate sensitivity. That is the last part. Okay. So what do you think? Whether the strain rate sensitivity should be low or it should be high? And low means how much low it is. Low, from low I mean that the point 1, and from high I mean it will be something greater than point 0.4 or point 0.3. It should be very high, right? If the strain rate sensitivity is high, then only what will happen, we have seen in the class, let us say this is our material and it got negged over here. So, and we know that the sigma y yield strength is equal to the some constant, let us say constant is k, strain rate, the whole to the power of m, that is a strain rate sensitivity. Now, if strain rate sensitivity is high, this particular term will be high and it will be difficult to again yield this particular section. And so what will happen? The remaining part will undergo the deformation and it will elongate to a larger extent. And that's how it should be. So, welcome. We just started with the first question. Okay. So here we can say that the grain side should be fine, strain rate should be low, and strain rate sensitivity should be very high. Okay. And so in this particular manner, our material will show the superplasticity. So if some material is given to you and people is asking that, okay, you tell me whether it will undergo the superplastic deformation or not. Okay. So what you will see, you will check its grain size, whether it's fine or coarser. You will check what is the strain rate you are applying. Okay. And also you have to check that what is the strain rate sensitivity of this particular material. Now, one question you will might think that how to find the strain rate sensitivity, M value, right? So let us say we want to find the strain rate sensitivity from this equation only itself we will find. So the equation is telling that the sigma y is equals to the some constant k times, and then there is a strain rate, the whole to the power of n. We'll find the sigma y in the case one. Let's say some we are putting some value which we have got from the machine, and we are putting the strain rate to be the epsilon 1. Now again we are dividing it by sigma y to k times strain rate 2 to the power of n. We can cut it out mathematically if we know all these values, which we will get from the experiments. Okay. So what we can say, we can take the log on both the side. We will get log of sigma 1 over sigma 2. It should be equal to the m times log of strain rate 1 over strain rate 2. Now you can move this over here, and that's how you will find the strain rate sensitivity. Okay. If someone want to go in little bit more detail about this particular strain rate sensitivity part, I would refer you the book George Dieter. Okay. And in this particular book, you can go to the chapter tensile testing. Yeah, tension test. And somewhere over here it will be. Yeah, over here. It will be on the page number 295. And from here, a couple of pages are usually based on the strain rate, and some little bit flavor of superplasticity is also given to them. Okay. In our course, we have not enter more of the mathematical point of view. Okay. So let's stick with this. So with that, we have solved the question number one, and we got to know the condition under which the particular material will undergo the superplastic deformation. Let me know if there is any doubt in this particular question number one. No. Okay, that's great. Let's move to the next question, question number two. Again, it will be very easy. Uh, so, so the question is telling that which of the following isn't the strengthening mechanism? Among this, which is not the strengthening mechanism? Uh, sorry, which are not the strengthening mechanism? There can be more than. Okay, so yeah, Venkatesh and yeah, grain size increment. Okay, it's option D, no? Grain size increment. Now, is there any more options which is not going to increase the strength of the material? See, if we increase the grain size, so the strength should drop down, right? We have seen from the Hall patch equation. Yeah, yes, Anisa, that is option E, annealing. So indirectly, we are saying, see, annealing, and if we do annealing, grain size will increase only. That's a method, right? So they two are clubbed with each other. I just put them one by one, one below the another, or else I could have directly put in bracket annealing. So these two are the correct option by which we are not going to increase the strength of the material. If we decrease the grain size, we have known that from the Hall-Fitch equation, sigma equal to sigma naught plus k upon root over d. If grain size is decreasing, this entire term will increase, and so our strength will again increase. So grain size reduction will increase in the strengthening. Solid solution strengthening, we know that if we put some uh, impurity atoms into the our lattice, then the dislocations, they will not be able to get the as similar atmosphere which it was supposed to get in the pure one, and so the dislocation will be impeded, they will be restricted onto this particular solid solution. Okay, the strain which is created by them. Okay, again the strain hardening is again one of the mechanism by which we can increase the stress. Like if you are creating more number of dislocations, now what will happen, they will pile up with each other and they will restrict their motions one. Okay, and with that these three are the strengthening mechanism, while these two are not the strengthening mechanism. Okay, so with that we have solved this question number two. Okay, let me know if there is any doubt in this. Okay, since there is no, let's move to the next question, question number three. If you see the assignments questions, they will also be like this, like very easy type. So now let's go to the question number three. Which of the following is not reduced by the grain size reduction? So, okay, which of these following things will not gonna decrease if we decrease the grain size? So we are decreasing the grain size, and among this, which is not gonna affect? Which is not gonna affect? Okay, C. Okay, yeah, elasticity is a, yeah, perfect, right, Anisa, yeah. So elasticity is something which is doesn't depend upon the grain size. Okay, I should have written the question. The question is somewhat not in the right way. Which of the following is is not gonna affected? Which of the following is not gonna affected by the grain size reduction? It should be like this. Okay. So we can say that yeah, elasticity is something which is not gonna affect because it will measurely what elasticity depend upon. Okay. So on what factor does elasticity depend? It depend upon the bond strength of the material, right? How the bond, how strong is the bond, right? So if we talk about the elasticity, so this slope is majorly depend upon the how the two atoms are bonded with each other. We have seen that if we draw the force versus resistance curve, then it will be something like this, and this particular slope is what determine the bonding. And force and distance, they are majorly we are talking from the perspective of the bonds, distance between the atom, and they are not going to affect by the reduction in the grain size. So let us say my grain size was this much large, and in another case the grain size was this small. In both the cases, we can say that the distance with the atoms which are there, the bond strength, sorry, the bond length in both of them will be exactly equal. It's not going to affect. And so elasticity is something, the factor which is not going to affect by this one. See, this question is very famous question, and oh, I put it over here. Yeah, this is a very famous question in the comprehensive exams. Okay, and in the gate also you will might find this question one or two times. Okay, and during my PhD interview, they have asked me this question. Okay, which is not gonna affect by the decrease in the grain size. Oh yeah, sorry. Let me know if there is any question, any doubt in this particular question. Question number three. Okay, since there is no, let's move to the next question. Question number four. The question is asking, that which of the following is a characteristic. Okay, they are telling about the characteristic of the superplastic metal. Okay, the superplastic metal we are having, and what will be the characteristic of that particular thing. So here the things are: strain rate sensitivity is given, it is low, then high strain rate, and low strain rate. What is your opinion on this? Like, we are given the material to us, this is a particular metal. What is its characteristic that it should show the superplasticity? A, B, C, or D? It is B. Oh, Anissa is telling it's low strain rate also. Okay, so let's discuss on these two things. See, we are given the material. Okay, now we already know that in the first question only we have saw that it's high strain rate and low strain. Sorry, high strain rate sensitivity and low strain rate. Low strain rate is something which we are providing to the material while we are deforming it, right? So we have to careful with this particular thing that it is something experimentally feasible, right? A same material is there. So what is the characteristic of the material from point of the material we are talking about, from the point of view of the metals? So this particular thing should have the high strain rate sensitivity. Okay. In the first question which we have discussed, we discussed the condition under which a particular material will show the superplasticity. Now, what is the characteristic of the superplasticity? It should be the high strain rate sensitivity. The sensitivity should be very high. So, majorly it depend upon the value of the M. So, this is a characteristic of the material for it to be the superplastic material. So, we are talking from the point of view of the material, not we are not talking from the point of view of the experiment. Okay, and that's why the correct answer is option B. Okay, and here it is. Okay, so I hope it's you are able to get it. Is there any doubt in this particular question? Please let me know. Is there any confusion in it? Again, we are talking about the characteristic of the metal. Okay, since there is no. Okay, no doubt. Perfect. Okay, then let's move to the next question. Question number 5. So, if you attend the final exam of this particular course, you will find the questions like in this particular sense only. It won't be so hard. Yeah. So now the question number 5. The strain rate sensitivity index, that is M, is given for the superplastic material. Is they are asking that in which particular range this particular M will lie. Okay. So they are exactly asking for the typical value that okay, uh, on what is the particular value of M should be, so that we can call it to be the superplastic. Like, what superplastic material will have the M value? So what is your opinion on this? We have this particular question has already been answered in the lecture. Okay, and it's actually it's P. Yes, it's right. So typically they will lie in the range of zero point 0.4 to 0.8. Yeah, it's B only. Right? Yeah, that's right. Answer is B. So what about this M, which is like A, point A? The first option, will it be so we are not calling, so since the M value is low, zero point 0.3 is again somewhat like transition. But if someone is saying that it's zero point 0.1, then what material? Yeah, it's a plastic material, right? It's not the super plasticity, it's a plastic. So instead of super plastic, then we will say that it's a plastic. And with that we have solved this question number 5. So let me know if there is any doubt in this particular question number 5. See how easy the things are. Like, most of the questions are exactly reflecting from the lecture which we have seen in this particular week. Okay, since there is no, let's move to the next question. Question number 6. So this is a question. It's a match the pair type. Now, one more condition we have missed to discuss in the question number one. Now I am thinking that I should have put in the question number one the temperature factor. Okay, so now we can discuss that. It's a mass of air type. On the column 2, we are having that A is a plastic deformation, B superplastic deformation. Here it's, let's say, let's mark them 1, 2, 3, 4, 5, 6, 7, and 8. Let's do one by one. Okay. Occur at low temperature. Plastic deformation or superplastic deformation? Which you think that will occur at the low temperature? A. It's a plastic deformation will occur at low temperature. If we increase the temperature, the mobility of the grain sliding, okay, and those things, diffusivity will be enhanced. Okay, the grain boundary sliding will be increased, and if so, at high temperature, we'll say that it's a superplastic deformation. It's not the plastic deformation. Okay, again, we have already answered this. Occur at high temperature, then it's a superplastic deformation. Involve dislocation movement. Let's see the fourth also involve grain boundary sliding. So now what about this? Involve dislocation movement and involve the grain boundary sliding. So three will match with among A and B. Which one? Oh yeah, three is gonna match with, yeah, perfectly right, with A. And so the grain boundary sliding will match with four is gonna match with the B. Okay. See, we are not saying that in superplastic deformation dislocation movement will not occur. Right now we are seeing what is a major mechanism by which these things are happening. Okay, and we know that plastic deformation will occur by the dislocation moment. In superplastics, some very small fraction dislocation moment can also occur, but majorly what will happen, the grain body sliding, and that's why we are matching with this. Now go with the 5 and 6, low strain rate and high strain rate. 5 which will match with A or B, which one? Again, it's a corresponding low strain rate. uh, High strain rate we apply. So think from this perspective that superplastic deformation, whether it should occur at the low or high. Yeah, Venkatesh. So 5 should match with the plastic deformation. So in superplastic deformation, what is happening? See, from this perspective that, okay, among plastic deformation, superplastic. So for superplastic deformation, we need, okay, you guys are right. It's for sensitivity. I missed this particular factor. Right. So it should have the high strain rate sensitivity. High strain rate sensitivity will be is associated with the superplastic, and the low strain rate is comparatively associated with the plastic deformation. Yeah, right. I was a little confused. I not read this particular sensitivity part. Now it's extremely easy part like 7 and 8. So what about 8? 8 is gonna match with A or B. Small will be there. Small elongation will be there in the plastic deformation, while the superplastic there will be the large elongations. Okay, and with that we have solved this question number 6. It was super easy. Only one factor we have introduced, like new thing which we have learned right now is that the temperature factor. Okay, remaining things we have already discussed in the previous part. Okay, with that we have solved this question number 6. Yeah, let me know, is there any doubt in this particular question? Okay, since there is no question, high superplastic. Yeah, since there is no doubt, let's move to the next question. Question number 7. Let me read it for you. The addition of the impurity atom to a metal lattice typically result in which strengthening mechanism? Oh, yeah, perfectly right. So this is option C, right? So the option C is the correct option. Now, if I ask you that why addition of the impurity atom, like initially let us say my lattice was somewhat like this. Now I'm introducing the new atom over here. I'm replacing this. Now what has happened that this thing like solid solution, if I include, it's gonna increase the, it is one of the strengthening mechanism. It's gonna increase the strength of the material, right? So if I ask you like what is the things is happening over here. So what is happening that let us say one dislocation is there, one dislocation is coming, and here that dislocation was able to again it encountered the same atom, same particular set of the environment is it got over here. Now from here it's saying that okay, this is the different atom, a different solution. It means that different stress field. It can either push this thing or it can also pull the things, pull the atoms, right? It can also like if the two atom was like this, now the new atom is coming over here and this two atom got far apart little bit. The stress field it can change from tensile and compressive it can change. Okay, it will not be like the initial one which was supposed to be in the perfect system. And now this stress field, if it is a tensile, sorry, if they are attracting each other, if the stress field of the dislocation and the stress field of this, they are favorable, they are attracting each other, then it will go and stick over here. And it's not gonna move anymore ahead because it's gonna restrict because now they are attracted with each other, now they are stick. And if they are repulsive in nature, okay, let's say it's this is having the compressive and this is showing the tensile nature. Again, this is having the compressive nature, sorry. So then in that case, what will happen? It will repel. Again, it will not let it to pass this particular region. And that is the reason why this is gonna increase the strength of the material. Okay. And what about the grain boundary strengthening? Grain boundary strengthening will usually occur when we decrease the grain size, right? Strain hardening we have discussed. Precipitation hardening. You guys already be knowing that what is the difference between solid solution and precipitation. It's like something is precipitating out of the material. Okay, something like that. So with that, question number 7 we have finished. If there is any, let me know if there is any doubt in this particular question. Question number 7. Okay, since there is no, let's move to the next question. Question number 8. Again, it will be like that, like same type of questions. Yeah. So the question is telling that which strengthening mechanism is primarily responsible for the increased hardness and strength of the metal during the cold working. We are performing some working onto the material. So among these three things, among these four things, which one is the primarily responsible for increase in the hardness and the strength of the material? Option one is okay. See, we are doing the code working, right? So, yeah, Anisa is telling it's A and Venkatesh is telling it's B. Gomaneti. Oh, it's very difficult to pronounce. Okay, yeah. So you are telling that it's D. Okay. See, we are not precipitating out first of all anything over here because we are just let's talk about one of the deformation mechanism, a cold working type. Okay. So let's take I have a metal block with me. No, I'm hammering it. I'm providing some code working to it. Let's say I'm hammering this. This is a copper block, and I hammer this particular copper block. Now, what is going to happen? Nothing is going to precipitate. First of all, that's clear because no new. We are not increasing the temperature. We are not increasing the temperature. We are not adding any other phases to it. Okay. So we can already remove this D, and we can also remove the solid solution strengthening. Also, we can remove. We are not adding any solution onto this. Now, the thing remains is the grain boundary strengthening and the strain hardening. Okay, so majorly now we are also thinking that okay, initial let's say this particular one was having the grain size of this sort, and after I deform this particular material, the grain size will be something like this. Let's say it is like this. The reduction in grain size will take place, but one more thing will happen that since I am providing lot of stress onto this, the dislocations will be created. A large dislocations will be created. This. Now the question is that which one among this is dominating, primarily responsible? Okay, that is the question. See, in the code working you are doing, you are decreasing the grain size also, you are increasing the dislocation density also. So A and B both are the right answer. But now we want to know that which among these two, right, Venkatesh? So both are the right answer, that both of them are gonna affect by the cold working. But among these two, which one is the primary? Which one is going to contribute more? Okay. So now think that you are having a copper wire with you and you bended it. So what has happened? Some grain size reduction occur, but on the major scale, what has happened? You introduce the tremendous number of the dislocations. The dislocation density, which was created, now it was very high, even though the grain size was reduced. But this factor is something which is happening to a very large extent compared to this. So, if in the question, if in the exam it asked that the code working is happening. So among these three things, among these four things, so let us say let's talk about this two thing only. So the strain hardening is the one which is gonna dominate over the grain body strengthening. So the correct answer, okay, see again, it's is. So we have to select any one which is a primarily responsible. So that is the strain hardening. So the cold working is on a major scale will gonna affect the strain hardening to a large extent, and grain bond reduction will also occur. They both will occur, but this is gonna happen by the large extent. Okay, so measure of this one will be the one which is responsible for the strengthening the cold working. Okay, so if there is any doubt in this question, let me know. If there is any confusion, if you want to have some debate that no, this should be the one which should be dominant. Right. So with that, we have cleared that the answer B is a right answer. And you can also remember this thing that like which one is going to dominate in the initial stage. So we can say that strain hardening is the one. Okay. So now let's move to the next question since there is no doubt. Let's move to the question number 9. It is going to be the most easiest question we have discussed it now. The Hall-Page equation relates the yield strength of a material to its A, B, C, and D. Again, only one answer is correct over here. It's answer B. Yeah, right. Yeah, all of you are correct. The answer B is the right answer. And the relation we have already discussed that. In the last week also we have discussed this. Right. With that, we can say that its Hall-Page relation is relating with the grain size. Okay. Let's move to the next question. Question number 10. Now, which of the following deformation technique lead to the reduction in the cross-section area? Which of the following deformation technique leads to the reduction in the cross-section area? Rolling, extrusion, forging, equichannel angular extrusion. So what do you think among this? Yeah, so extrusion is one. Yeah, Venkatesh. So you're telling that Venkatesh is saying it's B, initiation. Yeah, right. A, B, and C. All of them are going to lead to the reduction in the cross-section area. So in the rolling, what we are doing, we are having the few rolls. Majorly, let's only talk about from the perspective of the two rolls we are having, and from here we are getting the deformed material. Okay, so its cross-section area, which was initially, and the final cross-section area, they are different. Right here, it's comparatively thinner. What about the extrusion? We are putting some material. It's getting extruded over here. So from here materials are going, and from here it is coming out. And this is usually the a rough way to draw the extrusion. From here, we will get that the final product will have the lower cross section area. Forging, forging is none other than the hammering. Okay, from that perspective, we can think. So again, if I hammer the things, hammer this particular thing, its size is gonna change. And let's say we are hammering it in this particular direction, then this particular area is going to be reduced. The area will decrease. While the equichannel angular extrusion, if we talk about this thing, so what is happening over here? We are having the channel. From here, we are putting the material. We are pressing it, and again we are getting the material, something of that sort itself. So the overall cross section which was initially and the cross section which was final, it will maintain the cross section area. That. Yeah, it is gonna maintain the cross section area because the channels are the one they are having the same cross section. Right. And so with that we can say that option A, B, C are the correct answer to this particular question. Right. Let me know if there is any doubt in this particular question, question number 10. Okay, since there is no, let's move to the next question, question number 11. Now, again, it's related with the ECAP, equichannel angular pacing. What is the primary purpose of this ECAP? To increase the ductility of the material, to improve the machinability of the material, to refine the grain size of the material, and deep part is telling that to increase the electrical conductivity of the material. So, what do you think? Among all these options, which one is the correct option? Again, one word is used over here, that is. So only one answer will be the correct answer over here. So Anisa is, yeah, it's answer C. What about the other? What do you guys think? Is answer C is a right answer? Yeah, it is the right answer. Maybe A. Okay, let's discuss on this also. Option A. So think from the perspective that what is happening in the ECAP. Can I say in the ECAP it's a plastic deformation is happening? Answer me, yes or no. Is the plastic deformation is happening in this particular thing? No. See, ECAP, what we are doing over here. Let's see from this perspective. So this is what ECAP is. Let us say initially our material was like this. Now we applied some force on top of it. And we are getting some final product, but let's see in somewhat in the middle what is going to happen. Somewhere over here, it happened like this. Its shape has been changed. It has deformed, right? From here, it went to here. So, so we can say that the deformation is taking place. Now, what do you think? If I remove over here, let us say I dismantle machines, will this thing will turn again back to this? There is a metal I was having, the copper I put. I mean, I applied some load over here. Will it come from this particular state? If I dismantle everything, will it automatically come from this particular shape to this particular shape? Yes or no? Answer is no, right? It cannot come. And that's why, since it is not able to retain its particular shape, so we can say that this has been deformed plastically. So this there is a plastic deformation has occurred in this particular case. And let me tell you, this particular technique has come under the technique in a group in the class of the deformation process, which is known as the severe plastic deformation. That is, there's a lot of plastic deformation is happening. So this particular recap has known for the severe plastic deformation technique. Okay, it's one of the technique where the severe plastic deformation occur. So it's not only the plastic deformation; it's severely the plastic deformation is happening. Now, plastic deformation is happening. So what do you think is happening inside the material? There will be the lot of stresses will be created. There is a lot of dislocation. There will be a lot of defects will be there, right? What is the defects to the electrical conductivity? So sorry, I was thinking from this particular. So what defects will do to the ductility? Think that we are having the material, okay, annealed material, and it was showing the stress strain curve something like this. It was showing this much of the ductility. Now let us say D1. If I deform this particular material, if I put some plastic deformation, I did right. So I put some dislocation, I put some point defect into it. So now, what do you think? What is going to affect? What is going to happen? Let us say the material which got after deformation is showing the ductility D2. So now, which one? What do you think? What is the relation between the D1 D2? Which one will be more? Which one will be more ductile? So whose length will be more? Whether D1 is more or D2 is more? Whether it is follow this or it will follow this, or let us say D1. Okay, I should move it a little bit. Is equal to the D2. So all of you, what do you think? Which of this is going to happen after deformation? If I applied some stress to it, now whether it's going to be more ductile or less ductile, it's going to be less ductile, right, Anisa? So its length is going to decrease, due to its decrease. So ductility is going to affect. So wherever there is a plastic deformation is happening, we are deforming it, the material. We are what we are doing, we are increasing the dislocations to it, and that's why the ductility of the material will go down. So it's not going to increase, rather it's going to decrease the ductility. Let's also also see this particular option D. It will increase the electrical conductivity of the material. On what factor electrical conductivity depends upon? If I have a pure material and if I have a deformed material, which one will be having the more electrical conductivity? In order to know that, one thing we should know that the defects in the metal are acting as the scattering center, and they scattering center for the electrons. So if electrons were trying to pass, and now here the defects are there. Okay, defects means, let's say, the hole. Here there is atoms are there, and the atom was missing. Now the electron will not be able to easily pass to it. So now it will scatter in some other directions. So the defects are created, and these defects are going to be a scattering center for this particular conductivities to occur. And so the electrical conductivity will decrease. And that is the only reason, that is one of the reason that when we anneal the material, okay, let us say I was having one copper. See, so I did one mistake in my lab. What I did, I took the platinum wire, why I was having that, and I need to put that in the one of the alumina tube, just to pass the current through that particular tube. What I did in front of my supervisor, I just deformed the material. I was taking the platinum wire with me. It was like this, and what I did, I was playing with it, and I made it like this. I deformed it. So now my guides tell that, see, you have decreased its conductivity. So now what you will do? So from here I went to I deformed it. The only way to restore its conductivity is by heating it up. If I heat up, so this dislocation, this defect will be annihilated. That is a process of annealing, right? So we have to follow the process of annealing, and will again increase the conductivity. So wherever there is a deformation, we are decreasing its conductivity of the material. And so option D is not going to be the correct one. It will decrease. So with that, we have found that option C is the only option which is correct over here. Okay. Well, let me know, is there any doubt? We have discussed a lot in this particular question. Is there any doubt in this particular question? Question number 11. Okay. Seems that there is no. Let's move to the next question. Question number 12. Okay, I made a mistake. I just printed the same question again. I don't know where is my real question. Okay, let's not discuss about the question number 12. Let's move to the next question, question number 13. I don't know where my question number 12 went. I will check it later on. Yeah, here. ECAP is a primarily a hot working process, cold working process, both hot and cold working process, none of the above. What do you think? Whether it's hot working means we are working on above the recrystallization temperature or homologous temperature. Cold working, we are working below it, or one can even say that the room temperature. So what do you think? A, B, C, and D. Which one will be the correct option for the ECAP? Pardon me. So in ECAP, whatever we have seen, that the equal channel was there, right? And there was a material we are putting, and then we are applying the pressure. In this particular entire thing, we have never discussed anything about the temperature. Why is the case? Because this entire stuff of ECAP is happening at the room temperature. We are, or maybe very slight temperature rise will be there. So since it is happening at the room temperature, it is the cold working process. It's not the hot working, and it cannot be the both. So the only option is the correct one is the option B. Okay. So we can remember this part that ECAP is a cold working process. Right. Let me know if you want to discuss on this, if you have any doubt on this. Okay. Since there is no, let's move to the next question. Question number 14. Okay, yeah. This is a true or false, true and false, right? Let me hide it with someone. We'll do one by one. True or false, and this entire thing is about the ECAP. So the first thing, it's not, it does not introduce significant strain hardening. They are telling that it's not putting the so much strain onto the material, strain hardening. So what do you think? Whether my material is getting hardened up or not? True or false? Okay. Uh, is there any network lag? I think. Okay. Yeah. It does not introduce the significant strain hardening. That's true. Yeah. Both of you are right. Perfect. So A1 is true. Right. B. It can be applied to the wide range of material. Can we do it for the all metals? Thus, did we talk about any restriction onto it? No, there was no restriction. We can apply to the wide range of material. That is true. Now, it is a very low cost process. Does it require? Yeah, it is also true. We just need the two angular, equal angular channel, right? It produce product with a low strength. What do you think on this? Does it producing the product which is having the low strength, or the material which was initially was a low? It is false, right? Since we introduce, we are deforming it plastically. Yes, you are perfectly right. So three are true and one is false. So we are deforming the material, so we are increasing its strength, so we are not producing the low strength, we are producing the high strength. So with that, question number 14 is over. Okay. Okay, let's move to the next question, question number 15. I'm having just three more question, and we'll wind up after that. Okay. So very easily we can answer this question. The primary mechanism responsible for the grain refinement in ECAP is, so they are telling that you are doing this refinement by what? Was there any phase transition? Was the grain growth was involved over here, or the recrystallization was happening? Severe plastic deformation. Venkatesh, yeah, perfect. It's happening the severe plastic deformation. There is no recrystallization over here, right? And even if the recrystallization will happen, there will be the increase in the grain size. Sorry, the new grain will form. It's not going to decrease the refine the grain, right? Grain growth, we are talking about the refinement. Why to talk about the grain growth? Phase transition, there is no phase transition. We are not working on the any temperature. We are not increasing the temperature. So the phase transition is not happening over here. The only thing is that severe plastic deformation. Okay. Okay, then that's great. Let's move to the next question, question number 16. Here, uh, again, it's related to the superplastic material. In superplastic material, the formation of the neck during the tensile testing typically leads to. So they are okay. They are telling that there is a neck formation is happening over here. So among and increasing the yield stress at the neck. So the what is the yield stress of the neck? Sigma y at the neck. And this is a non-rec region. Let's say this is a sigma y. So which one is more, sigma y or sigma yn at the neck? It's C. No change in the yield stress, yield strength. Okay, you guys are telling that there is no change in the yield strength. Tell me one thing. Anissa is telling that increase in the yield strength at the neck. Yeah, Anissa, yeah. So the option A is the correct answer, right? So let's discuss why. Why the option A is the correct option? Why? So the yield strength is over here. So this is a yield strength for the material. The where the plastic deformation is starting. They are telling that okay, yield strength over here and yield strength over here. Which yield strength is quite higher? For that, we need to know that which one has deformed more. Whether it's neck which has deformed more or this. The more it will deform, more strength it will be having. Right? We can see from that perspective. So the one which is more deformed, we just now discuss a lot that if there is a deformation, there will be the more dislocation, there will be the more refinement in the grain size. Those things will happen, and so we can say that the sigma y will be more, sigma yn will be more. So the neck will be having the more strength compared to the this. One more thing, we have discussed in the class. Sorry, the professor has taught us that the yield strength is depending upon the strain rate to the power of m. Okay, so this is the equation we have discussed about. So from that also we are able to see that okay, yield strength is gonna increase at the neck point. Let me know if there is any doubt in this particular question. So the option A is the correct answer. So compared to the neck, these regions are having the lower yield strength, and so in the superplastic deformation, what will happen? They are the one which is going to deform. So this region are the one which are going to deform because they are having the low strength, and this one was having the higher strength, and that's why it is going to be deformed. This is not going to be deformed in the superplastic deformation, and that's all. And again, we are talking about the superplastic material, right? So for the superplastic material, in the case of superplastic materials, yield strength sigma y at the neck is higher, and that's why when the neck is formed, it will be the stable one. Its strength will be higher, and that's why it's not gonna decrease its dimension further. Rather, remaining dimensions will be decreased, and after a while, we will see that after a while of deformation, everything will be something like this. Okay, so neck was like this, and the entire thing now has gone like this. So this is what is happening. Okay. So with that, question number 16 is over. Now let's move to the last question, final question. Question number 17. It will be the very easy one. There are the few terms are there onto the left side, and onto the right side there is a unit. Before we start, I should have marked it. One, two, three, 4, 5, 6, 7, 8, 9, and A, B, C, D, E, and F. Okay, so tensile strength. Yeah, that's right. It's C. So the one is going to match with the B. Strain. What is the unit of strain? What do you think? Which one will be the correct answer? None. There is no units because strain is change in the length divided by the original length, and both of them are having the unit of the meter. They will cancel out. So the strain will not be having the any unit. What about the ductility? How the ductility is measured? Again, option D. Yeah, that's right. So again, it will not be having any dimensions. People usually write the ductility to the per meter, but again they are having the same dimensions. So we can say that it's not having the any unit. So the ductility is also going to match with the no unit. Modulus of elasticity, that is a sigma y. So they are sorry, not sigma y. That is they are talking about this slope. What do you think? Modulus of velocity, which unit among this, which of the unit it will be having? It will be having the NPA only. And he said, yeah, that's right. Why is it so? We know that the slope is nothing but is dy by dx. In y, what is happening? We are what is there? It is nothing but stress, and stress unit we know it is MPa. And in the bottom there is a strain, and we know that the strain doesn't have any unit, so there is no unit. So the overall we have got the MPa, and so with that we can say that this is going to match with the MPa. What about the resilience? Resilience. It is having the unit of the yeah, perfect right. It is A. What does it mean? Uh, any idea like what does it mean? It's the energy, right? Right. So we know that the stress strain curve it is goes something like that. Let's say this is a plastic deformation where it started. So the term resilience, which we have discussing that it is the energy which is absorbed during the elastic deformation. Okay, so this is this area, that is the area under the curve. So this area we are talking about. Okay, and this area will be the having the unit of this multiplied by unit of this. Okay, and that will be the joule per mm cube. See again, if someone can argue that okay, see this and this, they both are same only, ampere and joule per mm cube. But since here we are talking about from the perspective of energy, so I prefer to write the joule instead of going for ampere. Again, both of them are right. What is ampere? That is let's say Newton per. It will be having the unit of Newton per meter square. Let's add one more meter to it. It will be a force into displacement is nothing but the work, that is joule, and this is meter cube. So they are having the same unit, but their essence are different. What they are telling that their essence are different. That resilience is something which is related with the energy, so it's preferred to write in the terms of the energy. What about the toughness? Toughness is what? It's the area under the entire curve. It's like it will also cover the plastic deformation region. So this entire thing, and it's not going to change. Yeah, that's right. It's again A. So this is also A. Toughness is also A. Strain rate. So inside telling that it's E. Venkatesh is telling that it's D, strain rate. Okay, now let's see. Let's work onto it. Okay, Venkatesh is also telling that it's E. Strain rate is having the unit of the second inverse. Okay, and why it is so? Strain rate is nothing but the strain over time. How the strain is changing with the time. Yeah, and the strain is the one which is not having any unit, while the time is having the unit of the second. And that's why it's the second inverse. And with that, the 7 is over. What about the strain rate sensitivity? 8. Yeah, that was the strain rate is having the unit of the second inverse. That's right. Okay. Yeah, that's great. So we all are on the same page. Now, let's move to the next question. Question number D, strain rate sensitivity. Yeah, it's a D only. So the mostly it is not having the unit any unit. Just now, just few moment back, we have wrote about the strain rate sensitivity. Its formula, that is log of sigma 1 over sigma 2, the whole divided by log of epsilon 1 over epsilon 2. They are having the same unit. They will cancel out with each other. No unit at the numerator. They are having the same unit. They will cancel out. That is that they both of them are not having any unit, and still they are canceling out, and we are not getting anything. So it doesn't have any unit. That's why the eighth one is no unit. What about the fracture toughness? Fracture toughness is that right? And that's how it is. So that is the so see the toughness and the fracture toughness, they both are having the different unit. Toughness is having the joule per mm cube, and fracture toughness is having the milliampere per per meter to the power of 1 by 2. And that's how it is. Let me know if there is any doubt in this particular thing. Usually people get confused in the toughness and fracture toughness. Okay, and we have found that okay what their unit are and how they are different. So let me know if there is any doubt in this particular question, question number 17, and this is our final question. Okay, since there is no doubt, so okay, that's right. And thank you very much. One more thing I would like to tell you guys. Sorry, I want to ask you first before I tell. Can you please explain the question number 4 again? Okay, let me see the question number 4, what it was. 2 is there, 3 is there. And then question number 4. Okay, this question. Which of the following is a characteristic of the superplastic material? So, on what base you will tell that this particular material and like material 1 and material 2, and which of them is a superplastic material? What is the property of the material? Okay, so so Venkatesh, what do you think? According to you, let us say, what do you think among this should be the right answer? Like you are asking for the, you ask that okay, let's discuss about this. There should be some confusion, right? I want to know that what is that particular confusion. I think it's related with the question number 1 and 4 altogether. Let's yeah, if you want to unmute yourself, yeah, you can do that. Let me go with the question number 1 where it was. I think doubt will be arising from there itself. I should have kept it in the organized manner. Yeah, over here. See, yeah, over here we can see that the question number 1, what it is telling that Here we are talking about under what suitable condition a particular material will be the superplastic deformation it will show. One, it should have the it should have the finer grain size we have discussed. The strain rate by which we are applying to the material, or the rate at which we are straining the material, it should be low. And then at the last, we discuss about the strain rate sensitivity, and we said that it's high. So among these three things, one, two, and three, which of them are related with the material property? This is the experimental one, right? This is the one which is related with the experiment. This is not the one which is related with the material. Okay. So the one and three are the one option one grain size, and the strain rate sensitivity are those things. These are the things at which are related with the material. Okay. So the how our material is sensitive toward the deformation to occur. Okay. And so over here we are right now we are having that low strain rate and high strain rate. Low strain rate and high strain rate is something which is in the control of the experimental, right? If I am doing the experiment, it will be under my control. But what is the property of the material, which will be the on what basis this material will be known as the superplastic material? So the condition is that it should have the very high strain rate sensitivity, right? And that's how we can clear this confusion that these are the experimental things and these are the material property. So this is a material characteristic, and that what has been asked over here in question number 4. So okay, got it, perfect. So with that, question number 4 is over. Yeah. So one more thing, that is there any doubt in the lecture that has been in question number 7? Victory assignment. Could you explain what the two line equations are? Yeah, Anisha. So see, I remember that particular question. So there are the few things was missing. Okay. So right, the things was like one of the, if we have known that particular entire length, if we know this particular entire length what it is, then it would be easy to find this particular equation. Okay. So now let me give you the hint that how one can solve this particular question. Again, the range of the answer which was there in the which has been given, it's quite large. Like, okay, so even if you write 33 or 24, something like that, or within this range, it will be right. So in the question also itself, that they are telling that you just find out some rough estimation what the value it should be. So let's see from this perspective. I'm just going to give you the hint that how to solve it. So over here, d to the power of minus of 1 by 2. This is this means that this entire thing is having the zero value over here. X is having 0, and you can assume the material to be the very well annealed. Okay. So let us say roughly a well annealed material will be in somewhat in the range of the micrometer. Okay. Let us say few hundreds of micrometer. Now we are going to the nanoscale, and so here we can say that okay, its unit should be, let's say it's 100 of nanometer. From that, from this particular thing, so we were discussing from this perspective, right? So because the here it was increasing, then here it was decreasing. It means that this is a nanomaterial region. Now, since this is a nanoscale region, nanomaterial region, we can assume that this will be the, on rough and estimation, we can say that it will be 100. Based on this, you can find d to the power of minus 1 by 2 for both the cases, and you can calculate this particular length. So this length, if it would have been given, it would be much more. The value which we will get, it will be like the answer of the range shouldn't be very large. We would have kept the answer of the range should be very small comparatively. And in this particular manner, we can find this particular length, and slowly we can solve this particular. Since we know this particular point height, we know what is this. we will get this point, we know the slope, we will be able to write the equation, we will be able to write the equation for this, and we will find its intersection. Okay, so with that we will be able to solve. I did get the answer right, but the second line question was hard to get, and the value I was getting wasn't high. That was the side. It was around 30. Oh, it was around 30, right? Okay, and 30 is the correct answer. 30 is the correct one. I think the range was something like 24 to 33, somewhere in that particular range. The answer which was given. Okay, yeah. With that, one more thing, that is there any doubt in this particular not in this particular week content that has been discussed? I will organize this later on. No. Okay, then let me tell you a few things that let me stop presenting my screen. I will start and present my another screen. Okay. So a few things that the entire recording of this particular week has been is getting uploaded onto this particular channel of mine, and here we can have a 1 to 3 has been already over here. Week 4 also I will put. Okay. So if you want, you can always go through this particular link. Okay. And the second thing is that on this particular forum, NPTEL one, you will be getting the problem solving session. Here will be the survey. Okay. And you can click on this particular link. Let us say copy this link address. I will put it in the comment box over here. And you can fill up this link, and you can all like this will be reflection on me that okay, how I am teaching and how I can improve. I will get the update in this particular manner. And few more thing I wanted to discuss. Form filling is over, channel is over. Yeah. And for the exam date, let's see the exam date. I don't know, but somewhere it should be. Reminder exam date it has been extended. Yeah, see, exam date has been extended. So if you are not filled the registration, if you not did the registration for the exam, and if you are willing to do so, then you can always click on this particular go to over here and complete your exam registration. Okay. Okay, then with that, we can meet on the next dot solving session. It will be on the same time, Saturday, and we'll start from 3 p.m. Okay. Okay, guys. Bye bye. Thank you.